callback plus topic plus pipeline stage. Last episode we taught a network to read pixels into characters with a CNN and RNN and CTC stitching it all together. That was the last stop on the vision lap. Now the road turns toward language. And here's the very first wall you hit. Text isn't numbers. A neural network can't multiply the word great by a weight. So before any NLP model can learn a single thing, we live inside one pipeline stage, preprocess, and go deep. Today, how to turn raw strings into numbers a model can actually learn from. Quick reset on where we are. The vision chapters are closed. From here on, the inputs are sentences, reviews, paragraphs, and not one of them is a tensor yet. Text arrives as characters and characters aren't math. So we open the NLP lab by deepening the very front of the pipeline, collect, then preprocess. And for language, preprocess is where most of the real work happens. Get this stage right and everything downstream gets easier. First move, tokenize. We chop the text into pieces the model can count, usually words. This movie was great becomes 4 tokens. This movie was great. Now we have countable units instead of a blob of letters. Next we need a vocabulary, a fixed list of every token the model is allowed to know, each mapped to an integer. Keras builds it for us. Text vectorization, adapt, scans your whole corpus, counts the words, sorts them by frequency, and hands every word an index. The model never sees text again, only those indices. You could stop there and one hot encode each index, but one hot is huge and honestly dumb. 10,000 words means 10,000 long vectors that are almost all zeros. Worse, every word is exactly the same distance from every other word. Cat and dog are as far apart as cat and democracy. The encoding knows nothing about meaning. Embeddings fix both problems at once. Instead of a giant sparse vector, each word gets a short dense vector, say 16 numbers, and those numbers are learned. Meaning turns into geometry. Words that behave alike end up close together in the space. And the geometry is shockingly rich. Similar words drift into the same neighborhood. Directions carry meaning too. The famous one, king minus man plus woman lands right next to queen. The model never read a dictionary. It just learned positions that make its job easier. Teaser into Act 2 on next episode. That's the key idea. These vectors aren't handed down. They're learned by the task, trained on a job that needs to understand words, and the embeddings reshape themselves to help. So let's pick a job. We'll learn embeddings while judging whether a movie review is positive or negative. And along the way, watch Great Find Its Friends, Code Time, Act 2 Overview. Here's the whole file, about 60 lines across 3 pages. Page 1, a tiny labeled review corpus and the text vectorization layer. We adapt it, peek at the vocabulary and vectorize one sentence so you can see the integers. Page 2 builds a small model with an embedding layer and trains it on the sentiment labels. Page 3 pulls the learned vectors out, ranks the nearest neighbors of great, and draws the PCI map. Imports and a tiny data set. 12 toy reviews, 6 positive, 6 negative, with labels 1 and 0. Real projects use thousands. 12 is enough to see the mechanism without waiting on a download. The vectorizer, max tokens, caps the vocabulary at the 100 most frequent words. Output sequence length equals 6, so every review becomes exactly 6 integers. Short ones get padded with 0, long ones get truncated. Fixed length is what lets us batch. Adapt is the learning step for the vocabulary, not the model. It walks the corpus, counts, and builds the word to index table. Then we print the vocab. Index 0 is padding, index 1 is the out of vocabulary bucket, and real words start at 2. Sorted most frequent first. Our tiny corpus only has 25 entries total. proof it works, we push this movie was great through the layer and print it. Out comes 2, 3, 7, 13, 0, 0. 4 word indices, then 2 zeros of padding to fill the length 6 slot. Small numbers because our whole vocabulary is small. That's the words to numbers promise on screen. Now the model, text vectorization first, then embedding vocab size 16. Every index becomes a 16 number vector. Global average pooling 1D averages the word vectors into one review vector, and a dense sigmoid predicts positive or negative. Small, but it's a real classifier. Compile and fit. Adam binary cross entropy accuracy. A handful of epochs on 12 examples. Accuracy pins to 1 early and stays there. The loss is still middling, and that's fine. The point isn't a low number, it's that to push the loss down at all, the embedding layer is forced to send positive words one way and negative words the other. Harvest the embeddings. We grab the layer's weight matrix, 1 row per vocab word, and write a cosine similarity function. For great, we score every other word and sort. Outcomes: wonderful 081, excellent 078, fantastic 074. The model rediscovered a thesaurus just from the task. Closer plus teaser. Last, we squash those 16 dimensions down to 2 with PCA and plot every real word. Positive words gold, negative words magenta. 2 clean clusters. That picture is the lesson. Meaning became geometry. And notice what we just built. A model that reads a review and learns words good enough to judge sentiment. Next episode, we make that the headline act. Real IMDb data, 50,000 reviews, positive or negative. Words as vectors put to work